Okay, by my watch, it's 1 o'clock, so I'd like to get started. Hello and welcome to the webinar. I'm Greg Johnston. I'm a Senior Application Specialist with Sensors and Software. This is part 2 of the webinar on the basics of GPR data interpretation. If you've not seen part 1, I encourage you to watch it sometime. But here's a very quick review of what we talked about in the last webinar. In part 1, we learned that every material has a property called dielectric constant, and different materials have different values. GPR reflections are caused by contrasts in dielectric constant. The bigger the contrast, the stronger the GPR reflection. This means that GPR cross-sections are really images of subsurface contrast. Any GPR cross-section shows strong and weak reflections depending on the amount of contrast between the object and the host material. GPR signals are attenuated as they travel into the subsurface. Attenuation is caused by the electrical conductivity of the soil. Soils with high electrical conductivity can absorb GPR signals in 1 meter or less, while soils with low electrical conductivity can allow GPR signals to travel tens of meters before they're completely attenuated. When looking at a GPR cross-section, point objects or linear objects crossed perpendicularly create hyperbolic responses in the GPR image. The actual location of the object is the top of the hyperbola. When the soil is layered such that the materials above and below an interface have different dielectric constants, energy is reflected and seen as a boundary reflection. The top of every GPR cross-section will have 3 or 4 horizontal bands from the direct air and ground waves. This is GPR energy that traveled through air or along the ground surface and arrives at the GPR receiver a few nanoseconds after the GPR transmitter fires. This energy does not enter the subsurface and can mask very shallow events. The direct arrivals are often removed using a background subtraction filter. The other type of signal seen in GPR data is the background radio frequency noise. This appears as snow or hash at the bottom of the GPR cross-section and is visible after the GPR signals have been attenuated. The noise comes from other sources of radio frequencies that the GPR receiver records. The background noise is random, making it look very different than the GPR data. Another way of saying random is to say that the signal is not coherent. The depth of penetration achieved by a GPR system at a given location is determined by finding the depth where the GPR signals have attenuated down to the same amplitude as the background noise, so it can no longer be detected. This point is also called the noise floor. I'd like to start part 2 now, and I'm going to start by talking more about hyperbolas. When we see a hyperbola in our GPR data, we know that there's an object in the subsurface, and by moving to the top or apex of the hyperbola, we can pinpoint the position of that object. However, at this point, one of our questions might be, how deep is this object? One of the nice things about a hyperbola in your GPR data is that it can be used to determine how deep the object is. Here's a little bit of math to explain how this works. Remember that GPR systems do not collect data in depth. They collect data in time. A GPR system is a very accurate clock that measures the time it takes the signal to travel from the transmitter into the subsurface, reflect from an object, and return to the receiver on the surface. A GPR system measures this time very accurately. In fact, it can measure this time to thousandths of a billionth of a second, or picoseconds. This is 10 to the minus 12 if you're mathematically inclined. This is a very accurate measurement of the travel time of the signal. The time it takes for the signal to travel depends on two things: the speed the signal is traveling and how far it has to go. Obviously, if the speed is slower, it takes more time to get there. And if the speed is faster, the total time is shorter. Similarly, the further the signal has to travel, the longer it takes. This is not rocket science. The problem is, we do not think in terms of time. If I ask you to dig a hole to 29 nanoseconds, that does not mean much to you. We need to convert the time values to a depth value. To convert from time to depth, you can see from the formula here that we must know the speed or velocity the signal is traveling in the subsurface. This is where the hyperbola comes in. The shape of the hyperbola is a measurement of the velocity we need. This is a beautiful thing. Most of you are going to be familiar with hyperbola velocity calibration. This feature is on all our GPR systems, so it can be done out in the field. It's also in the Echo Project software, so it can be done once the data is transferred to a PC. If this is new to you, the idea here is to interactively fit the shape of the red hyperbola to the hyperbola in the GPR data image. Here's a chart of the GPR signal velocities in various materials. I want you to note that air is the fastest material. A velocity of 0.3 meters per nanosecond is also 300,000 kilometers per second, which some of you will know is the speed of light. GPR signals in air travel at the speed of light. 0.3 meters is 30 centimeters, or about 1 foot. So it's handy to remember that the speed of light is about 1 foot in 1 nanosecond. We're going to use this later in this webinar, so keep this tucked in the back of your mind. Speed of light is 1 foot in 1 nanosecond. Continuing to look at the velocity values in the chart, notice that the slowest material besides metal, which is an exception, is water down here towards the bottom of the table. GPR signals travel 1/9 the speed of light in water. So the presence of water in soil has a huge effect on the velocity of the soil. It also affects the contrast of the soil, as we discussed in part 1 of this webinar. Note the range of velocities you can get in soil. Clay, silt, and water-saturated sandy soils all have very low velocities, 0.06 meters per nanosecond or lower. This is because of the presence of water in the soil. On the other hand, dry soils have very fast velocities, up to 0.15 meters per nanosecond. This is half the speed of light. So soil velocities can vary a lot, from less than 0.06 to 0.15 meters per nanosecond. If you take the average of the soil velocities, you end up with 0.1 meters per nanosecond, 1/3 the speed of light. This is a good average value to use when you get to a site and have not measured the velocity yet. So let's look back at the velocity that was measured on this hyperbola from earlier. When I zoom in on it, you can see that it came out to a value of 0.116 meters per nanosecond. Going back to the velocity table, this suggests that it is a drier than average soil with a velocity close to limestone. It is a reasonable velocity for soil. Now, when I say that we have used the hyperbola to calibrate for velocity, what specifically have we measured the velocity of? We've not measured the velocity of the object. Some will say that we have measured the velocity of the soil around the object. This is true, but not exactly true. The truth is, we have measured the velocity of the soil above the object. We don't actually know the velocity of the soil deeper down. So if you're given the choice of doing a velocity calibration on a deep or shallow hyperbola, choose the deeper one, as it will provide a better overall velocity for the soil. Now let's show you an example of the velocity calibration so you can see the effect on the GPR data. Here's a GPR line that shows a number of objects, so you can see the hyperbolas in it. It's about 26 meters long and goes down to about 4 meters or so. The depth scale on the left side is calculated using a velocity of 0.1 meters per nanosecond. This value is used because they just got to the site and have not had a chance to calibrate for the actual velocity. If we check the depth of the leftmost hyperbola, it comes out to about 1 meter. Now, let's use that hyperbola to calibrate for the velocity. We fit the curve, and it turns out to be 0.44 meters per nanosecond. You can now see that in the depth scale. Looking back on the table from earlier, you'll see that this is the velocity of a very dry soil. The depth scale is now updated using the new velocity. Now let's check the depth of the leftmost hyperbola again. It is now about 1.45 meters deep. The depth estimate is much more accurate because we are using the measured velocity of the soil and not just guessing. Velocity calibration usually gets you to within 10% of the actual depth of the object. Now, I want you to notice that when the velocity was changed, the GPR image did not change. Only the depth scale on the left side changed. It's important for me to say here that all this stuff about velocity and hyperbolic calibration does not matter if you do not need to know the depth of the object. Some people, especially utility locators, tell me that they do not give out depth information for various reasons, mostly around liability. So if you don't care about depth, measuring the velocity and worrying about the velocity setting on the GPR is not important. In fact, you can have a velocity setting that is completely wrong, say set to the speed of light, 0.3 meters per nanosecond, and still find and accurately determine the position of an object. As you see in this case here, the image has not been affected one bit, only the depth scale. So at the speed of light, it appears that this, the leftmost hyperbola is about 3 meters, but that's only because of an incorrect velocity setting. Let's talk about the effect of the shape of a target. Before we discuss shape, I just want to remind you of something we discussed in part 1 of this webinar. Remember that GPR energy does not just travel straight down like a laser beam. It radiates in a cone under the GPR system. This means that as you move a GPR system along the surface, there's GPR energy traveling ahead of you and behind you that can reflect from subsurface objects. Let's start with a round object like a pipe or an underground storage tank. The nice thing about round objects is that GPR energy always hits it at 90 degrees, so it reflects right back. The result is that round objects produce nice hyperbolic responses. I think everyone who has used GPR knows this. If you think about it, the width of one side of the hyperbolic tail is how far away the GPR system was from the object when it started to detect it. In favorable soils, this distance can be 1 or 2 meters. Now, this is not critical information to know, but it may be of interest. Let's look at what happens with a square-shaped object. As we approach the object with the GPR and energy goes out ahead and hits the object, where is that energy going to go? GPR energy behaves just like light, and we know what happens when light hits a mirror. The angle of incidence equals the angle of reflection means that the GPR energy that hits the side of a square object is going to reflect downward, and no energy will reflect back to the surface to be recorded by the GPR receiver. This means that a square object is not detectable with GPR until the GPR is right over top of it and can bounce energy off the flat top. Once the GPR is past the square object, the same thing happens as approaching it. GPR energy traveling behind the GPR reflects from the side of the square object and reflects downward. So the response from a square object, like a buried foundation wall or a duck bank, will not be a hyperbola with long tails. It will be a flat response. Now, you will get slight hyperbolic responses off the edges because of the corner reflection, but nowhere near as strong as a round object. The lesson here is that different shaped objects will produce different responses in the GPR line. Here are examples of the responses from many different shaped objects. I collected this data at the University of Tennessee at Knoxville. They dismantled a car and buried the parts in a field for the geophysics students to detect and map out using various technologies. Many of the objects show hyperbolic responses, but you can tell that some of the objects are oriented at an angle because of the distortion of the hyperbola. For example, this one and this one and this one all look like that object is sitting at an angle. The two that I find very interesting are the one that looks like a bird and the one that looks like a braid right beside it. I wish I knew the shapes of these parts. Another point that is related to shape and responses, and is also very near and dear to my heart, is that whenever you are collecting GPR data, collect long lines. If your client is paying you to collect data over an area that is 10 feet by 10 feet, make sure you collect at least 1 or 2 reconnaissance lines that are 100 feet long that go through that 10 foot by 10 foot area. It is so important to put the area of interest into context. In this example, imagine if they only collected a 4-meter long line from 14 to 18 meters. That would make this strong reflector around 1.5 meters deep a normal part of the area, when in fact, we can see that clearly this 4-meter stretch is different than anything else around it. Long lines always help your interpretation of the data. For conquest customers who do concrete scanning, whenever possible, I suggest you use the 4-foot grids and not the 2-foot grids. I want to discuss a response that is usually only seen when dealing with utilities, and specifically non-metallic pipes. We know from part 1 of this webinar that GPR energy will not transmit through metal. This means that you will only ever get a response from the top of a metal pipe. But that is not the case when the pipe is non-metallic. GPR energy can travel inside the pipe and reflect from the far side. The result is a second hyperbola that is perfectly parallel to the first hyperbola. So we see the reflection from the top, the hyperbola from the top part of the pipe, and the reflection from the bottom of the pipe. Some people wonder why you get a second hyperbola when the top of the pipe is convex in shape and the bottom of the pipe is concave. The answer is to remember that the only difference in the travel paths of the GPR energy is 1 diameter of the pipe. So you get the same hyperbolic shape, just later in time and therefore deeper in the GPR line. Now, some of you are thinking, if I can see the top of the pipe and the bottom of the pipe, I can determine the diameter of the pipe by taking the difference. It's a good idea, except for one thing. Unless the pipe is full of soil, the GPR energy will change speed when it gets inside the pipe. This means that the distance between the top and bottom hyperbolas will change depending on the material inside the pipe. For example, if the pipe is full of water, the GPR signal slows down as it goes through the pipe, and the reflection from the bottom of the pipe takes longer to get back to the receiver. The result is the bottom hyperbola is further from the top hyperbola. Or, if the pipe is full of air, the GPR signal will speed up to the speed of light inside the pipe, and the hyperbola from the bottom of the pipe will be closer to the top hyperbola. So you can estimate the diameter of a non-metallic pipe if you know the velocity of the material inside the pipe and are willing to do a bit of math. In this example, say the reflection from the top of the pipe is at 20 nanoseconds and the reflection from the bottom of the pipe is at 30 nanoseconds. You get these values from the depth scale. We need to know the time the GPR energy was in the pipe. So we take the bottom of the pipe time and subtract the top pipe time. Now, if you think about it, the energy actually traveled the diameter of the pipe twice, once on its way in and once on the way out after it reflected. So to get the one-way travel time in the pipe, we have to divide by 2. When we do the calculation in this case, we get 5 nanoseconds. That is the total amount of time that the GPR energy was inside the pipe. Now, the diameter of the pipe is determined by multiplying the speed of the material inside the pipe by the one-way travel time. If the pipe is water-filled, we know the GPR speed of water is 0.033 meters per nanosecond. When we multiply 0.033 by 5, we get 0.165 meters, or about 6 inches for the diameter of the pipe. Now, if the pipe is air-filled, we know the GPR speed of air is 0.3 meters per nanosecond. When we multiply 0.3 meters per nanosecond by 5, we get 1.5 meters, or about 58 inches for the diameter of the pipe. So you can see there's a tremendous difference depending on what the material is inside that pipe. That's why it's so critical, if you're going to try to do this calculation, to know what's inside the pipe. So that's how you do this calculation if you ever want to do it in the future. Now, thinking about this, I don't even want to think about this calculation if the pipe is not completely full. Imagine a pipe that's half full of water. Let's move on. If you have a layer on the surface that has a very strong contrast with the material below it, GPR energy can become trapped in that layer and reflect up and down many times. We typically call this response a Ringy response. An example of ringing is what you see when you collect data on a frozen lake. The contrast between the ice above and the water below is so large that the reflection coefficient is very large as well, about 67% if you do the math. As the energy bounces several times, you see the same reflection repeated. So here's the bottom of the ice, here's the first reflection, the second reflection. So the second, third, fourth, etc., those reflections are called multiples. So you'll hear the term multiples used when you get this sort of ringing or multiple bouncing inside a material. Now, I suspect that there are not too many people in my audience doing ice profiling. So let me show you another situation that you are more likely to encounter, a puddle of water. Here is the response that you will sometimes see when collecting a GPR line through a puddle of water. Again, there's a large contrast in materials when going from water to asphalt, and the reflection coefficient is about 57%. So the energy can bounce in this layer several times. When you look at this image, it's important to remember that even though the reflections in the puddle and in the ice look like they are coming from deep in the subsurface, that energy has not traveled past the first layer in the ground. The multiple bounces take more time, so the response appears deeper in the GPR line. But the energy does not travel to the depth indicated. In this case, you can tell that this is a water puddle because look at the direct ground wave at the top of the section. GPR signals travel so slowly in water that the direct arrival between the GPR transmitter and receiver along the surface through the water takes much longer compared to when the GPR is on the asphalt. So you can actually see it dip down. This is called a velocity pull down. Now, the reflection in this case of the water puddle does not repeat as cleanly as the ice data does because the puddle has edges and we are also getting reflections from the water-asphalt interface. So it looks pretty messy. Now, a big caveat here. Please do not take from this that you cannot collect GPR data on a wet surface. You can. The puddle ringing only occurs when you collect data through a puddle deep enough to submerge the whole bottom of the GPR antenna, so there is no air underneath. So use your GPR in the rain. Go through across wet surfaces, but understand what you're looking at if you get an odd response when you go through a puddle. Okay, now that you have learned that GPR energy can become trapped in a layer and bounce many times, let's go back to the non-metallic pipe we discussed earlier. If you look at the bottom of the GPR data image, you can see the top of a third hyperbola. The first hyperbola is the reflection from the top of the pipe. The second hyperbola is the reflection from the bottom of the pipe. Where is this third hyperbola from? It is caused by GPR energy that bounced inside the pipe, just like in the ice and in the puddle. Here's an animation of the path the energy took that formed the third hyperbola. And note that this can happen many times. You will sometimes see 4, 5, 6, or even more hyperbolas caused by GPR energy becoming trapped inside a non-metallic pipe. The key points here are that all the hyperbolas will be identical in shape, perfectly parallel, and equally spaced. Because remember, the only difference between them is one diameter of the pipe. Okay, you recall in part 1 of this webinar, we discussed the responses of a linear object, such as a utility. When you cross a linear target perpendicularly, you get a hyperbola. But when you run along the top of it, parallel to the path, you get a flat or sloping reflector that can easily be misinterpreted as being a boundary reflection if you're not careful. But now I want to talk about point targets, single objects in the ground. Now these are objects, single point objects are probably not too interesting to utility locators, but they are interesting to archaeologists and forensic investigators. Say you had a buried cannonball and you went over it with a GPR. What would you expect to see? I think most of you would say a hyperbola. And you would be right. Now, what happens if I cross that cannonball at a 90-degree angle to the first line? What would I see? I hope at least some of you said hyperbola again. And again, you would be right. In fact, what differentiates a point target from a linear target is that no matter how you cross it, you get a localized hyperbolic response. I'm sure that the utility locators out there have experienced something like this. You see a strong hyperbola, So you assume it is a linear target and run a parallel line off to one side to see if you see it again. You don't. So you go to the other side of it and you run a parallel line to see if you see it on that side. You don't. You chase it around for a while before you realize that it is a single object buried in the subsurface. I once had a concrete scanning customer tell me that they were so baffled by this point object that they saw in the concrete that they chipped out the concrete and found a wrench that someone had dropped into the concrete as they were pouring it. I want to discuss a special point object that you will see a lot if you use GPR in urban areas. Small, shallow metal objects, usually metal debris that is left in the subsurface after construction. It is a special object because of the response that it creates in a GPR section. What happens is that as the GPR transmitter passes over the metal object, GPR energy gets onto that metal object and turns it into an antenna. The GPR energy travels back and forth along the metal and re-radiates the GPR energy, just like an antenna. The result is what we call a metal ring. Here's two examples of what ringing metal looks like in a GPR section. The response repeats over and over, just like the ringing we saw earlier from ice and a puddle. And just like the ice and the puddle, even though the responses from the metal look like the GPR is seeing deep, it is not. The energy is trapped on the metal and just bouncing back and forth. The multiple bounces take a longer time, so the response appears deeper in the GPR line. The energy does not travel to the depth indicated on the depth axis. Note that you will get this same ringing if you cross a piece of metal on the surface, such as a manhole cover or a metal wire. Also note that this response only occurs from metal of a small finite size. Crossing a 500-foot long shallow metal pipe will never give you a response like this. Yes, the GPR energy can get on that 500-foot long pipe, but by the time it travels 500 feet and reflects from the end and comes back, the response is not likely to be picked up by the GPR. Now, we have already discussed that the shape of a hyperbola can be used to measure the velocity of the soil. But what does it mean when you do a velocity calibration on a hyperbola in the GPR line and you get a velocity of 1 foot per nanosecond? If we look at the table of velocities, we see that 0.3 meters per nanosecond, or 1 foot per nanosecond, is the velocity of air. So what's going on here? Over the years, I've had people say, if the velocity of the hyperbola is the speed of air, the hyperbola must be from an underground cavity, tunnel, or void. But remember, the velocity we have calibrated is not the velocity of the object. It is the velocity of the material between the GPR system and the object that created the hyperbola. So if we get a velocity of 0.3 meters per nanosecond or 1 foot per nanosecond, this means that the object that created the hyperbola is in air. This is called an air wave. In this particular example, the hyperbolic response was caused by a street light passed during the survey. Even if someone tells you that their GPR antennas are shielded, GPR energy can leak out into the air and reflect from objects like buildings, trees, poles, and fences. Now, before you get all worried about airwaves in your data, remember that with a little due diligence, they are quite easy to interpret. Have a look at this example. We see hyperbolas in the top part of the section, and we see other hyperbolas in the bottom part of the section. But notice how much broader the deeper hyperbolas are. If we do a velocity calibration on the shallow hyperbolas, we get a velocity of 0.1 meters per nanosecond. a third the speed of light, and a typical velocity in the ground for a moist soil. However, when we do a velocity calibration on the deeper hyperbola, we get a velocity of 0.3 meters per nanosecond, or 1 foot per nanosecond, the speed of light. This hyperbola was caused by an object on the surface. One story I have to tell is the rental customer who was upset with us because he had found in a very remote area a response from what he thought was an underground tunnel. I'm pretty sure he was a treasure hunter. He subsequently paid a guy with a backhoe $10,000 US to transport the backhoe to this remote area and dig a hole 7 meters deep. Surprise, surprise, he didn't find anything. So he thought that our GPR system was faulty. He sent me the data to look at, and guess what? He had dug for an airwave. I told him that learning to recognize airwaves is GPR 101. A basic training course would have saved him a lot of money and a lot of aggravation. Getting back to this image, here's a challenging question for you. How far away was the surface object that caused the airwave on the GPR line? Think about that. Let me give you a hint. You can answer this question if you look at the time scale on the right side of the plot and remember that the speed of light is 1 foot in 1 nanosecond. You got the answer? Let me help. The top of the hyperbola occurs at about, let's call it 54 nanoseconds. So how far away is the object? Some will say 54 feet, but those that do are forgetting that the time scale is a two-way travel time. It is the time required for the GPR energy to travel from the transmitter to the object and reflect back to the receiver. So, to get the right answer, we have to divide the answer in 2. If we do that, 54 divided by 2, 27 feet. So if I went to this GPR line and I stood at about the 44 meter mark, right on top of this airwave, and I looked 27 feet away, there would be some object that caused that airwave. You can also get airwaves generated by walking up to an object, usually a sizable object like a building. If you see airwaves, they will look like a sloping reflection as you approach the building. The good news is that you can use the hyperbola fitting to measure the velocity and see if they are airwaves. You just have to place half the hyperbola off the screen and just use 1/2 of it to do the fitting. The trickier airwaves to interpret are those that do not create a hyperbola, so you can't use hyperbola fitting to detect them. In this example, there's a strong reflector at about 30 nanoseconds that looks a little suspicious. So to do my due diligence, I'm going to check and see if there's an object like a building or a fence running parallel to the GPR line about 15 feet away. This is one of the reasons why taking photographs of the site, using GPS so you can go in on Google Earth is really valuable for detecting airwaves. Another airwave to be aware of is the reflection from an object above your head. Power lines running across an area can appear as airwaves in your GPR data. In this example, a GPR line was run under an underpass under a building. The strong flat-lying parallel reflectors only occur in the part of the line under the building. The reflection occurs at a time of about 18 nanoseconds on the time scale. This suggests the underpass is about 9 feet high. It also looks like the energy bounced twice because there's a second response that mimics the first response at twice the depth. Again, this would be called a multiple. I have seen many people interpret airwaves as objects or boundaries in the ground. with a little homework on your part, it is not a mistake you should make. When people first learn that some of the reflections they see in a GPR line may not be in the subsurface, but caused by airwaves, they usually get a bit worried. I need to point out that airwaves are typically very weak reflectors, just a bit stronger than the background noise floor we talked about earlier. What this means is that they are masked by those strong, real reflections from subsurface objects. It's only when the GPR signals have attenuated down near the background noise floor that the airwaves are visible. If we go back a few slides, that's very prominent in this one here. You can see that these airwaves are surrounded by the background noise. So they're just a little bit stronger than the background noise. But in this particular case, somebody gained up their section enough that these very weak reflections look very strong. And that's when the problems start. So if you see GPR signals fading out and then suddenly there's a stronger reflection, be suspicious of that reflection. I am not saying to automatically interpret it as an airwave, but use what you've learned here to determine whether it is above ground or a below ground object. I want to talk about large diameter objects. I've included this topic because someone who attended the last webinar asked me to cover something about interpreting underground storage tanks. Here's an example of an object with a very large diameter beside an object with a very small diameter. It is not hard to notice the difference in the width of the hyperbolas. When an object gets physically very large in diameter, the width of the hyperbola increases. Now, you may think that you might confuse the hyperbola from a large diameter object with an airwave. You won't. But you do need to modify how you do a hyperbola velocity calibration on a larger diameter object. The hyperbola fitting method is based on the object being a small point object. So when you do a hyperbola fitting on a hyperbola from a large diameter object, you have to match the shape to one side of the hyperbola, not try to fit it to both sides at the same time. If you fit it to one side, you will get the correct velocity and therefore get better estimates of depth. For our utility locating audience members, I would like to discuss interpreting utilities in trenches. I think I mentioned in part one of this webinar that when working in soils with high electrical conductivity that attenuates the GPR signal before it can travel very deep, sometimes you can locate the utility by finding the trench it was buried in. The utility may be too deep in the trench to detect it directly, but finding and mapping the trench is almost as good. In this example, the GPR penetration in the trench is much deeper than the native soil. It looks like the trench was backfilled with a different material, a material more favorable for GPR. Notice the X-shaped response at the top of the trench. This is a characteristic response for a narrow trench. Let's look at another example. In this example, we see the same sort of X pattern from the trench. You can also see the hyperbola from the utility deeper down in the trench. I have an animation that shows why a narrow trench results in an X pattern. It comes down to the GPR signals reflecting from the far side of the trench as you approach the trench and move away from it, similar to our earlier discussion about round objects and hyperbolas. When the GPR is on the left side of the trench, it sees the reflection from the boundary below it and the far side of the trench deep in the GPR line. As the GPR moves, the far side of the trench gets closer and the reflection moves shallower in the GPR line. When the GPR reaches the middle of the trench, it gets reflections from both sides of the trench. As it moves to the right side of the trench, it now gets reflections from the left side of the trench, starting off shallow and getting deeper and deeper as it moves further away. Hopefully that's a bit of an explanation on why you see this sort of thing. A very common mistake that people make is the bottom of the X looks an awful lot like a hyperbola itself. So they interpret that as being the utility. And it turns out the utility may be deeper down. The last topic of this webinar is noise. In part one of this webinar, I talked about random noise. This is radio frequency noise from other sources like radio stations, communication towers, cell phones, walkie-talkies, the universe, the sun, lots of things generate radio signals. You recall this slide, which shows that once the GPR signals attenuate to the same level as the random noise floor, that is the depth of penetration. I will also set up a future webinar by mentioning that random noise can be suppressed by stacking the data. If the noise floor is lowered, that means we can see the GPR signals deeper and therefore increase the depth of penetration. This is what our new pulse echo ultra receiver does. More about that in a future webinar. I would like to talk more about noise, but this time a different type of noise. I want to talk about the signals in GPR sections that GPR manufacturers don't like talking about. This is called coherent system noise. As the name suggests, it is noise created by the GPR system. As such, to some extent, it's within the power of the GPR manufacturer to engineer out of their products. But in my opinion, many GPR manufacturers do not do a good job of this. Have you ever seen flat-lying signals in your GPR data like the ones in the examples I'm showing here? The left one is data from, it's an image from a sensors and software system, while the right image is from one of our competitors' systems. The important lesson here is that very flat reflectors in your GPR data are more than likely not real signals from the subsurface. They are coherent system noise. But they can look like boundaries. And if you are looking for a boundary, like maybe you're looking for the water table, which you expect to be flat, these bands fit very well. Again, I've seen many GPR practitioners interpret coherent system noise as real subsurface reflectors. Once you put a colored line on a reflection, everyone believes the interpretation. If you see flat reflectors in your data, be suspicious. Mother Nature is not like that. If you are collecting data over undulating ground and you have flat reflectors in your data, they are almost certainly coherent system noise and should be ignored. So what causes coherent system noise? It is caused by poorly placed metal cables or metal housings that get energized when the GPR transmitter fires. And similar to what we saw with the shallow metal debris, re-radiates the GPR energy. These signals appear in the GPR data usually as banding. This shows a plot of how we want to generate a pulse that goes into the ground. In an ideal world, we would like that pulse after it's finished to go to 0. Unfortunately, this is impossible with electronics, so you will always have some system ring down. What separates the great GPR systems from the poor GPR systems is the amount of ring down. Unfortunately, many people get convinced by slick marketing that shows GPR data in areas that are favorable for GPR. The ground response, shown in blue, is so strong for so long that it can easily hide bad coherent system noise. That's the signal shown in red. It is only when you try the GPR system at a site with high signal attenuation that you can see the coherent system noise. So when you are using your GPR system in tough conditions with high attenuation, be very cautious about interpreting the signals you see as being from the subsurface. If you see lots of coherent system noise, ask your GPR supplier about it. I also want to point out that because system noise is coherent, it cannot be reduced or eliminated by stacking. No matter how many times you stack, kilo, mega, giga, tera times, stacking will only make the coherent system noise stronger. So this is a good reason why you want a GPR system engineered to have a low amount of coherent system noise, so you can take full advantage of stacking to see deeper. The usual fix for coherent system noise banding in GPR data is applying a background subtraction filter. This filter can hide many sins, but I think that some GPR manufacturers are too dependent on software filters to fix poorly designed system hardware. Sometimes coherent system noise turns out to be something that can be easily fixed. In this example, you can see the banding on the left image. The banding is gone on the right image. It turned out to be poor placement of a GPS cable. It was picking up the GPR signal and re-radiating it. Moving it away from the GPR antennas eliminated the system noise. This completes part 2 of the basics of GPR data interpretation. But before you go, just like we did in part 1, let's have a quiz to see what you've learned. So question number 1. How many utilities in this image? Good look. Look at the hyperbolas. Count the number of utilities. 82% of you said 2 utilities. I have a really smart audience. 2 utilities, I think, is the right answer. I wouldn't blame you if you pick 4. So the 6% of you that said 4 targets, I thought that for a long time. And then one day somebody pointed out to me that these hyperbolas are perfectly parallel to one another. So you have one here that's perfectly parallel. So the interpretation is this is the top of a non-metallic utility and this is the bottom. And then you have a second one where you're seeing top and bottom. So I think the correct answer is 2. So well done. How many targets on this image? So the answer is 2. The answer is 2. And if you look at the description here, you've got target 1 on the top, and then the second target is all 4 of these hyperbolas. So the top one is top of target 2, bottom of target 2, first multiple in target 2, second multiple in target 2. So 32% of you got that right. 62% of you said there was a single target there. The thing to watch out for is that these hyperbolas are not equally spaced. The 4 below are equally spaced, but the one above is not equally spaced with any of the others. And that's why it's treated as a second object. The other thing to see is that the hyperbola is not perfectly parallel. The response from the top target has a different hyperbolic shape than the 4 underneath of it. Okay, moving on. So here's another one. I'll explain this one a little bit more. A borehole in the area reports that the water table is at a depth of 10 feet. Is the strong reflector that we see at about 10 feet here, 60 nanoseconds, likely the water table? Yes or no? Pretty even split here. 53% say no, 47% say yes. I want to give you a hint. Have a look at this. So pretty even split, but this little hint here gives you an indication that something is not quite right. The shape of the hyperbolas that we see just above this flat-lying reflector that we think might be the water table is the speed of light. How does that work? Let me give you the strongest hint. Let me put this data into context, which is the right thing to do. This is where the data was collected. It was collected inside a warehouse. And so the reflection that we see at 60 nanoseconds is actually the ceiling, the metal ceiling. And the hyperbolas that we see just above the reflection from the ceiling are actually the steel girders holding the ceiling up. A little bit of a trick question. What you need to notice in this image is that the GPR signals are really fading out. And by the time you get down here about 40 nanoseconds, you're into the background noise. And then all of a sudden you see these strong reflectors appear. And again, I mentioned earlier that airwaves appear kind of out of the noise. So a bit of a tricky question, certainly because the data was out of context. Let's move on to question 4. There's 10 questions, by the way. Question 4. So based on the fact that that is the ceiling, how high is it? Correct answer is 30 feet. 48% of you got the right answer, but 37% of you said 20 feet. I'm trying to guess. Maybe you took the 10 and doubled it and came up with 20. The way you're supposed to do it is remember that the speed of light is 1 foot in 1 nanosecond. So you go to the time scale, you look at the time the reflection occurred, and you take half of that. So 60 nanoseconds divided by 2, 30 feet. That's the correct answer. Hopefully you followed that. Okay, next question. Here's a cross-section that shows some interesting responses. What could be causing these reflections? 75% of you got the right answer of disturbed soil. 18% of you talked about high attenuation. High attenuation removes signal, it doesn't add. Now perhaps you're talking about the high attenuation in these areas. The way I would approach this, if you struggle with this interpretation, and this is a tough one, there's no doubt about it. Again, it's out of context. Start with what you know. You can look at this section and you can say, I see a bunch of hyperbolas. And hyperbolas are from objects in the ground. So let me sketch out some things that look like an object, one for each hyperbola that I see. And this is what you end up with. You end up with a sketch that looks like this. Now, if I remove the GPR section from it, you get a sketch that looks like this. And hopefully that leads you to look at this and say, well, yeah, okay, this looks like some sort of trench or ditch or something that's been filled in with materials like rocks or something. And if you look at the answers that are provided, the closest thing to that sort of situation is a disturbed soil. And that's what it is. It's disturbed soil. And when you replace the material back into it, you're producing all sorts of clumps of dirt and voids and rocks and things like that that have not been placed in the way they were before, and therefore end up being a very strong target for the GPR. Okay, most of you got that one right, so good. So moving on. This one should be a short one. Which target is not round? 1, 2, 3, 4, or 5? 97% of you said 4, and that is the correct answer. So 4 is a flat-topped object. You could see the flatness. It's actually a 45-gallon drum, steel drum on end. Okay, next question. Did this GPR line end near a utility, or is this an air wave? And I'll point out there is enough information on this image for you to determine whether it's a utility or an airwave. Think about it. Think about the things we discussed about airwaves. Very even split. 53% said airwave, 47% said near a utility. The correct answer is near a utility. Now, let me go through how we come up with this. This is determined without having to do a hyperbola fitting to determine the velocity of the soil. We strongly think that the hyperbolas on the left, the hyperbolas that we see up here shallow, the ones that are very strong and well above the noise level, are real objects in the ground. So if these are real objects in the ground, then compare the angle of the tail to this object to the angle of the tail of the questionable hyperbola. The angle is the same. And so if the angle is the same, the velocity is the same. And if you think that this one's in the ground, then this one's in the ground as well. And that makes it a utility. Okay, next question. Question 8. Could this be a coffin buried 6 feet deep? Look at the image, think about it. Let me give you a hint. Unlike the other one that I didn't get managed, let me give you a hint on this one. We measure the velocity off of the tail on this, and we get 0.3 meters per nanosecond. Most of you have voted, and overwhelmingly you say no. It can actually, 90% of you say that no, it's not, and that's the correct answer. So in this particular case, it's an air wave. And here's an example. Here shows the context of where it was collected. So somebody walked underneath the canopy, energy reflected off the canopy, and then they came out the other side. The other thing to look at is the distance. If you notice the edges, this starts about 75 feet and ends at around 120 feet. So if that's a coffin, it's a very, very big coffin. So the answer on this one is no, it is not a coffin. Okay. Question 9, which hyperbola is the best one to calibrate on? Number 1 or number 2? So if you're going to do a velocity calibration, which one are you going to pick? Okay, I'm actually surprised. Let me close the poll on this one. I'm surprised. It's quite an even split. 56% of you said number 2, which is the correct answer. But 44% of you said number 1, which kind of surprises me, because I mentioned earlier that what you want to try to do, you want to pick the deeper hyperbola. The deeper hyperbola is going to be the one that gives you the velocity of all the material above it, which gives you a better overall velocity for the soil. And maybe you're thinking about the length of the tails or the fact that this tail's going off the edge. That makes number 1 better, but in my opinion, it would be number 2. All right, last question. It's a tricky one. It's a bonus question. In the concrete data image, the bottom of the slab disappears in the middle. You see the reflection and then suddenly it's gone in the middle. What is the most probable explanation for this? There's a few different options here. What is the best explanation on why you cannot see the bottom of the slab in the middle part of the section? 37% of you gave me the right answer. The slab is thicker in the middle and the bottom is visible further down. You can actually see a response further down. The slab does get thicker in this area. Now, 56% of you gave what I think is a pretty good answer based on the level of knowledge, which is the amount of reinforcement is hiding the bottom, which is true. It's actually not a topic that we covered. That's what makes this a really tricky question, because so much energy is being scattered away by all these hyperbolic responses from the rebar that you have less energy to go down and reflect off the bottom. And I think that was the reasoning there. And that's a pretty good answer. It takes a lot to notice that if you look in between the rebar, you can actually get a few peaks at the thicker part of the concrete deeper down. That completes today's webinar. I hope that you've learned something useful to make you a better GPR practitioner. And thanks for attending. Feel free to contact me with any questions that you have using the email address listed on the screen. Bye for now.